Good afternoon, ladies and gentlemen, and welcome to today's lunch hour lecture. My name is Jack Ashby from UCL Grant Museum of Zoology, and I'm here as your host today to welcome our speaker, Dr. Chris Briley from the Geography Department here at UCL. Chris spends most of his time researching the past 4 million years of modelling the last 4 million years of climate data and the relationships between hurricanes, typhoons, and climate change, as well as running the MSc program in climate change in the Geography Department here at UCL, which places him perfectly to give today's talk on a world with this much CO2. And also it comes particularly timely with what some people are calling Wild Wednesday yesterday. So if, with no further ado, I'll introduce and welcome Dr. Chris Briley.
Thank you very much. Thank you. So what I'd like to talk to you about today is some of the research that I've been doing, looking at the climate of many millions of years ago. And the first thing I'll start off by talking about is talking about carbon dioxide levels. And hopefully you'll then realise why the climate of 4 million years ago might be interesting. And then I'm going to go on to talk about the early Pliocene and the climate of that time and how we know about the climate of that time. And then move on to the bit that I find particularly interesting, which was trying to understand why the climate looked like that. And finally, I'll just sum up and give some final thoughts. And so I'm going to take a series of figures and information from the Intergovernmental Panel on Climate Change's report. So the Intergovernmental Panel on Climate Change has been effectively commissioned by all of the governments in the world to summarise the state of climate change science over the and how it's moved over the past few years. And this summary, the first tranche of this summary on the physical science basis of climate change, was decided upon in September and released and is just about to be printed. It's been decided how it's going to look, and the book is being printed at the moment. And the book for this first third of the report is about yay thick, so a good inch or so thick, and then because that's quite a lot of information, that's summarised into a technical summary of only about 50 pages, which is then summarised into a summary for policymakers of only about 12 pages, and then from that summary of policymakers, a few headline statements have been drawn. And I'm going to include some of those headline statements. And so these statements are not controversial, and they're not new. They're what the state of climate science is. And so the first one of these is that carbon dioxide concentrations have increased by 40% since pre-industrial times. And this comes primarily from fossil fuel emissions and secondarily from land use change. And here and on the screen, I'm just showing you the instrumental record of carbon dioxide changes. And carbon dioxide is a well-mixed greenhouse gas, which means its lifetime in the atmosphere is an awful lot longer than the time it takes to mix the atmosphere, which is on the order of a couple of months. And so you can take one or two measurements of carbon dioxide around the globe, and that gives you a good number for what the value right the way around the globe is. And what you can see here is that when we first had an accurate enough instrument to be able to measure carbon dioxide concentration levels, it was round at about 315 parts per million, and since has increased dramatically over the past 60 years. And in March last year, you can see how there's an annual cycle here. The red line has a peak and a trough throughout the year. And last year, the annual maximum peaked over 400 parts per million for the first time in human history, or at least in the first time in the instrumental record is what you can see from here. But because you only need one measurement of carbon dioxide to get the carbon dioxide level across the whole world, what it means is you can take carbon dioxide measurements from bubbles that are trapped in ice cores, and because we have ice core records that go back an awful lot longer than the past 60 years, that can give you information about what carbon dioxide levels were like beforehand. And so before we really started playing around in the climate system, the carbon dioxide level was 278 parts per million. And then as you go back in towards the depth of the last glacial cycle, so when ice was covering Scotland and approaching towards us down in here in southern England, about 20,000 years ago, the carbon dioxide level was down at about 185 parts per million. Now, the longest record of ice core record we have comes from Antarctica and goes back 800,000 years. And you can see how the climate goes into a cold period and then comes out of it, or at least you can see the carbon dioxide emissions or the carbon dioxide levels appropriate to that. And what you can see here, there's 800,000 years, so there's about 8 glacial interglacial cycles here, and the level goes down to about 185 parts per million and up to about this sort of 280 parts per million. And so there's a range of about 100 parts per million. And this is what we've got sort of confidence in, this concentrations going right back through 800,000 years. And so we're able to state with a really high confidence that the atmospheric concentrations of carbon dioxide and also methane and nitrous oxide, I'm not showing you those, but they're other strong greenhouse gases, have increased to levels that are unprecedented in at least the last 800,000 years. But so how far back do you need to go to be able to find a carbon dioxide level equivalent to what we're breathing today? And so this is a collection that I published last year looking at different ways of estimating carbon dioxide going back in the past. And once the ice core, once you get to the bottom of the ice in Antarctica, then you have to infer the level of carbon dioxide from some indirect measure. And so those indirect measures have error bars. And so, for example, the orange estimate is looking at the stomatal size of fossil leaves. Okay? And so there are a variety of different estimates. And so there's this low period where carbon dioxide's down about 185 parts per million, oscillating up and down for the past million years. And then when you go, and then as you sort of travel back in time, there's the ice age cycles still continue. I'm not showing you that here. But the ice age, the glacial cycles, they only really start happening about 2.5 million years ago. And before that, there was no glacial, sort of glacial interglacial cycles, and the world was permanently in sort of an interglacial, a warm period. And that corresponds to higher levels of carbon dioxide. And to find somewhere where you can sort of effectively say that the majority of the records approach 400 parts per million, and even then we're not really sure, and maybe it's not. It's about 4 million years ago, at least that's the time period I'm picking. So the Pliocene goes from about 3 million to 5 million, and there's a geological epoch that encompasses all of that. So we reckon some stage in the Pliocene, there was a carbon dioxide increase of 400 parts per million, right? And I find it very hard to envisage timescales and thinking back that far. So I asked my daughter if I could borrow her little Playmobil. And so if this Playmobil person represents a person's lifetime, then let me put her down on the floor, then me, being roughly 6 feet, sort of is Roman Britain. So when London was sort of being founded, and then to go back to the time when there was a vast ice sheet, you've got to compare this. You've got to compare the Playmobil person to, say, Canary Wharf. Will take you back to there. And if you want to get all the way back to the Pliocene, then you need to compare something like this Playmobil person to the Matterhorn, right? A really large mountain. And so that gives you some idea of just how far back we're looking here. Right? At least it helps me slightly. Okay, so how and what do we know about the climate in the past? And so what I'm showing you here is today's sea surface temperatures. And as you can see, it's the hopefully you all realise that it's warmer nearer the equator and gets colder towards the poles, and the warmest waters are over by Indonesia, and then it gets colder as you head along the equator over towards Peru, right? And that's just today's sea surface temperature data. But on top of this, there are some black dots, and each one of those black dots represents a long sediment core, right? And so the way we extract information going back, this sort of continuous records going back of 5 million years, is you go out into the ocean and you drill down a couple of miles of the ocean floor and pick up that mud, effectively, divide that mud into various samples, and then you get, or in my case, you get a colleague to look down a microscope to extract particular microfossils of a single species, and then you can sort of boil those down in a geochemistry lab, boil them down and measure the respective ratio of the magnesium and the calcium in each of those little microfossils. And we know that the magnesium to calcium ratio is proportional to the temperature at which these animals lived, and they're going to be living at and we're individually picking ones that live at the surface of the ocean, right? And so we can create proxy temperature records going back over the course of millions of years by doing this lab work. Okay, and I don't expect you to really even, I guess, be able to read all of this, but this is all of the data from long time records that we have going back to approaching 5 million years ago. And each one of these lines is from a particular location in the ocean core, and effectively it requires an awful lot of man-hours just to be able to get one of these lines, right? And so we've now got a series of information, and I've categorized these lines as roughly the oceanographic conditions that they're in. And so in the top left, you can see all of the data that we have for regions that have the warmest sea surface temperatures at present. And so those are sort of the concentrated, that pool of warm water concentrated around Indonesia. And hopefully you'll be able to spot that as you go forward go back 5 million years, the temperature doesn't change. It's fairly consistent. And then the top right and bottom left figures are showing records that are in regions where cold water approaches the surface. And cold water also brings up nutrients when it's upwelling, and so these are invariably regions of high productivity and are particularly good for going off and getting nice long sediment records. And so they pop up quite a lot in the geological record, or in the records in sort of the composite that I've done. Right? And so you can see that the present day, so over at this end of the figure, if that's showing anyway, the present day, you start off with colder temperatures, so modern temperatures, and then on this very long-term average, as you head back millions of years, it's starting to warm up, right? And it's starting to approach the same temperatures as are occurring in the warm pool, and you'll need special eyes to be able to read the scale bars at the side. I appreciate that, but nonetheless they are, right? And the high latitudes and sort of everywhere we know is warming up, apart from these very warm waters. And so, rather than showing you lots of lines, I thought I'd give you a nice image. So this is my schematic of what this Pliocene climate might have looked like, just for the annual mean sea surface temperatures. And instead of having warm water sort of surrounding Indonesia, you end up with this pool of warm water spreading right the way across the Pacific and probably across the Indian Ocean as well. And that warm water's spreading right the way across, and then also expanding out towards the poles, and the high latitudes are warming up an awful lot. Right? Later in this talk, I'm going to show you some difference plots. So I ought to just show you the difference between this schematic and the present day one. And bear in mind, this is more just a schematic rather than a precise estimate of what the actual temperatures were, because we only know the temperatures at those 20 sites across the whole globe, and so I've needed to do some filling in, right? But you end up with temperatures that are pretty much the same in the warm pool, and then where that cold water upwells on the equator and by the coast of Peru, you're seeing dramatic warmings of about 5 degrees warmer. Okay, and so that's effectively saying that there's no temperature gradient east-west in the Pacific. And then the mid-latitudes are warming up a lot more than 5 degrees. We have some records from the Arctic showing approaching 20 degrees worth of warming, going back sort of these sort of 4 million years or so. Okay, so I've got this schematic. We've got this vision of a world 4 million years ago that just has this vast pool of warm water sitting in the middle of the Pacific, and that's structurally different to what we see today. And I can ask, with the help of an atmosphere-only model, right? As Jack said, I'm a climate modeler, so I do a lot of work in model world rather than going off and getting my hands dirty and digging up the sediment cores myself. But knowing this sort of this picture of the changes in temperature, I can then go and insert those underneath an atmosphere, and to be able to say, okay, well, what would the consequences of that sea surface temperature pattern be? And I guess I don't expect you to understand these figures. They're more to remind myself exactly what I'm supposed to be talking about. So don't worry if they seem a little bright and garish. The circulation in the tropics consists of a very sort of thin band of clouds and associated rain running actually slightly north of the equator, but think of it as being on the equator because it's easy to describe. And that's because that's where the strongest energy from the sun is coming, and it's sort of coming in and it's focusing on there, and that's leading to a warming and hot air rising, and so you get these big sort of clouds forming in this thin band right the way along across the equator, and that's forming rain. And hopefully in the top plot on the right, you can see a very bright red band. So this plot on the right is showing the rainfall or the precipitation in both the present day and the Pliocene. And if you look at the top one, you can see this thin band of very strong precipitation, and that's where this air is uplifting. And it goes up, it reaches the top of the sort of the effective atmosphere, and then heads out towards the pole, sinks down, and then flows back in. And it gets to about 30 degrees north. This circulation is referred to as the Hadley circulation. Right? And as that air is sinking down over the sort of the desert regions, it's going to be stopping any convection and precipitation occurring, or reducing the amount of precipitation that's occurring in those regions. And so this sinking air, as part of this large-scale Hadley circulation, is going to be explaining the desert regions, and so the purple regions in this top plot, right? So you get this sinking air over the Sahara, say, and the uplift, right? Looking back in the Pliocene world, where you have temperature, where you have warm water everywhere, you lose the focus of this circulation. Right? And so you end up smearing out the rain across the tropics because it doesn't know it. It's not quite so focused. It's warm everywhere, so convection can occur everywhere. And you end up sort of dramatically reducing this Hadley circulation and spreading the rain out in different places around the world, and removing some of these vast desert regions. And also, and this is just an annual mean picture. There are going to be changes in the seasonal cycle as well, and so changes in the monsoons are contingent with that, right? And that's sort of one broad scale picture of the climate. But it's not just these annual mean pictures that are important when we think about climate and climate change. And so I've had a go at estimating what you might expect tropical cyclones to do. And tropical cyclones is the broad term that covers all of the phenomena. So hurricane, typhoons, cyclones in the Indian Ocean. And they're all the same thing. And And what we've had to do here, we've had to do some statistical downscaling, where we take information from the atmosphere the atmosphere run that I've just shown you, and seed little storms in that, and watch where those little storms would flow, and then calculate the intensity along the track of those little storms. Effectively, it's fairly complicated. Just to say that where there's warm water in the present-day ocean, the warmest waters are where tropical cyclones occur in the present-day ocean. And if you had warm waters right the way across the ocean, tropical cyclones would be expected to occur right the way across the ocean. And so this is actually 2 years worth of data here, for both synthetic data for both the present day and for the Pliocene. And I hope what you can see is that there are tracks right the way across the ocean. Wherever there was warm water, there's now these hurricane tracks. So they're more pervasive. I'd be surprised if you can pick up is that the average strength of a hurricane has grown larger. The strength is sort of indicated by the color, but it's hard to pick that sort of stuff out. So the average strength has grown larger, and the lifetime of these storms has also increased. And partly that's because they're now forming further out into the Pacific, and so they're able to travel for longer before they hit some land. Okay, so that's a description of what sort of the Pliocene climate would have looked like. And certainly in the tropics, I've only focused on the tropics. I really just do the tropics, so that's all I'm going to talk about today. But this Pliocene climate looks quite different. And what I think is a really interesting question, and one that you can start to get a handle with model world, because you can change things in model world that you can't change in real world, is to ask, okay, so the climate was different, why was it different? And what could have caused these changes? And so the first test you'd want to do is to say, okay, well, we know that the boundary conditions, so the inputs I have to feed into a climate model, were different. And so I'll feed those slightly different inputs into a climate model and see what happens, right? And so, for example, we know that the sea level was higher back in the Pliocene, and we don't know exactly how much. I'm going to take 25 meters for this study. But estimates range from 5 meters to 40 meters. Nonetheless, the implication is that there's substantially more sea level rise than just losing the Greenland ice sheet. There's definitely a contribution coming from Antarctica as well, and the Antarctic ice sheet being a lot smaller. Okay, so there's sea level rise that we can feed in that sea level rise. We know that there have been both climatically driven, but also evolutionary changes in vegetation over the time period. And in these models, I need to specify what the surface of the land is. And so we specify some changes in vegetation. And having said that, we know that there must be some contribution from the Antarctic ice sheet being smaller. You would need to go in and change the size of those ice sheets. And I've already showed you right at the beginning, I guess I sort of motivated this whole talk that carbon dioxide levels were higher, and so we'll put in a level of, actually we're using 405 parts per million of carbon dioxide in this study, but nonetheless. So we're going to take those as inputs and feed them into a coupled climate model. And what I mean by coupled climate model is it's one that's got an atmosphere, an ocean, some sort of land surface, and sea ice that are all just, they sort of exist by themselves. They're solving the physical equations of those, sort of describing that fluid, that particular fluid. And I don't need to tell it anything about the ocean. It's going to derive all of the properties of the ocean for itself. Okay, so I'm just feeding in these inputs and seeing what's happened. Now, this particular study that I'm showing you is a model into comparison study. And again, I don't expect you to really even be able to read the pictures here, but it's a model into comparison study. So 8 different climate models have all been run with the same boundary conditions. And in this case, it's focused at 3 million years ago, and I was talking about 4 million years ago, and I certainly concede that there's a difference between the two. Yeah. But nonetheless, it's a good starting point, right? And so there's these 8 different climate models, and they've all been fed some of these changes that we know, that we're certain happened. And I think, hopefully, this is the change in temperature. And you can see that some of these have some very strong changes in temperature. The scale bar goes up to 10 degrees here. And so this is not a negligible amount of climate change that's going on. But nonetheless, none of these are showing a 5-degree sort of warming in regions of the Pacific, and so they're not showing the change in structure that the paleo estimates of the climate were showing, right? So that these models are not really fitting with the data. And so, again, I want to ask the question why, and for me, this is quite a fundamental question, because there are sort of two different possible explanations. There's probably 3, right? You could either, in fact, the data could be wrong, but I don't think that's the case. So it could be that we're feeding the wrong information into the climate model. So the climate model is responding to the wrong factors, or it could be that the model itself is responding incorrectly to the right factors. And which one of those it is might have an implications for future, right? Because if I'm asking the wrong question of the model and feeding it the wrong information, then of course I'm going to get the wrong answer, and it doesn't matter, right? But if the models themselves are not giving climate changes in the correct way, then that makes me worry a bit about that would make me worry a bit about future changes. Okay, so having said all of that, I'd like to talk about the two major suggestions of how you can reconcile sort of the observations of the Pliocene and the model could end up falling into discussions about exactly how we know the land, where the land was back 4 million years ago, and how the models are responding to carbon dioxide feedbacks. Okay, and I'm going to test all of those suggestions in exactly the same model so I can compare them all. I've got my obligatory climate modeling slide telling you the details of the particular climate model. You don't need to remove all of the acronyms. Just understand that this is one of the most sophisticated models, but I'm having to run it at quite a low resolution so that I can do enough long runs. But this is one of the models that is going to be included that has been included in the most recent IPCC report. Right. So the important bits of ocean gateways or changes in land, sort of where the land is, that have been hypothesized to be interesting are the ones that connect different oceans. Okay, and so the Indonesian through flow is very complicated to model at the moment. There's the deep sort of the flow of water from the Pacific right through the little channels in Indonesia out into the Indian Ocean is fairly complex, and the region is quite tectonically active, and so there easily could have been changes in the sort of going over the course of 5 billion years. The Bering Strait, the connection between the Pacific and the Arctic, probably was closed about 5.5 million years ago, was definitely open at 3, and then is closed sporadically once you start getting big ice sheets on North America sucking the sort of sequestering the water out the land, right? It's only very shallow. And so that changes at times. The most important and most discussed change is the connection through Central America. Central America has only emerged over the course of, say, the past 20 million years. So the connection between the Atlantic and the Pacific is very important. And so I can feed all of those changes into my coupled climate model and see what impact they have. And remember, I'm looking for a warming of 5 degrees off the coast of Peru. And certainly none of these have that's change. So Indonesia, which is the top corner, and then the Bering Strait don't really do anything in the tropics. I've not applied a sort of a statistical significance test because I don't like showing white plots. This stuff isn't relevant. These changes are just weather, effectively, or the climate version of weather. Changing the connection between the Atlantic and the Pacific Oceans does have a really strong climate effect. And you can just sort of see that poking through the top of this top plot on the right. Right? It completely alters the circulation in the North Atlantic, which is going to lead to a big seesaw and a change in sort of north-south temperature gradient. But nonetheless, it doesn't do a vast amount in the tropical Pacific, right? And remember that the tropics is half the world. Half the area, the surface area of the globe fits between 30 north and 30 south. Okay, so these gateway experiments, they easily could have changed, but they're not going to be the explanation for what we're seeing in the tropical Pacific and what the reconstructions suggest. And so that leads me to explore some of the suggestions about how models are responding to carbon dioxide. And before I show you the sort of stuff I've done, I thought I ought to show you a sort of canonical response of a climate model to an increase in carbon dioxide. And so in this case, I'm using this same model, and I've increased carbon dioxide by 100 parts per million. And it leads to a global warming. There is warming everywhere. That warming is much stronger near the poles, and it's stronger on land than it is over the ocean. Right? That's the pattern associated with greenhouse gas changes. Okay? Now, when I was describing the climate to you, I suggested that there were a lot more hurricanes. Now, hurricanes, if you've seen some pictures, and hopefully you haven't been in one, you'll have seen that they're quite windy, and they mix the surface layer of the ocean up quite a lot. And in doing so, they actually take some of that heat and use it to sort of power themselves. But the majority of but they bring cold water to the surface and they push heat down underneath, right? And certainly the climate model I'm using, most climate models don't have the resolution. They're too coarse to be able to get full-on hurricanes in them. They can get things that you can sort of detect and think are hurricanes, but they don't get full-on hurricanes in them, just because the hurricanes are quite a small feature. The amount of mixing that the ocean sees in response to a hurricane is related not to how fast, to the maximum wind speed, it's related to the Q of the maximum wind speed. And in fact, it might even be related to higher things. So insured losses are related to the 9th power of the maximum wind speed, right? So just making your hurricanes a little bit stronger can really make a big difference, right? And so I know that there's a potential for the Pliocene having a large amount of mixing in the upper ocean that is not being captured by the climate model because my climate model is not capturing hurricanes. But that doesn't stop me going in and just injecting some mixing, right? It's unphysical, but I can go and do it to have a quick explore as a sort of sensitivity study. And so in this case, I've injected some mixing in 2 bands where I was seeing the strong hurricanes. And this is a substantial amount of mixing for a quiescent upper ocean. Okay, and this is the change in temperature in response to that mixing, and that mixing, sort of by bringing cold water to the surface, is bringing some hot water, is moving warm water down to sort of 100, 200 meters depth. Think of this as Hawaii, sorry, over in this region from the figure, you'll know where Hawaii is. Right? And it's moving, so it's cold water at the surface and it's moving warm water down underneath. And there's an ocean circulation that takes sort of that subducted water, it takes it right the way across at about 100 meters or 200 meters depth, all the way across to the Philippines, where it hits the coast of the Philippines, gets entrained in a boundary current, hits the equator, and then zooms along the equator and emerges in the cold region off the coast of Peru. Okay, and so you end up with, so by injecting this mixing, I'm able to create a very warm, sort of a very preferential warm water on the equator, where we were seeing 5 degrees of mixing, 5 degrees of warming from the data. I'm only getting 2 degrees here, but at least it's a step in the right direction, right? And so hurricanes are one sort of potential feedback that's missing. The other one is relating to clouds. We get clouds. Clouds are really awkward to do in a climate model because they're very small compared to the scale of a climate model. But we know they're important, so we need to include them. Exactly how you include them changes from model to model, and so this is from a recent Nature News and Views, and so all of this is 5 different climate models all responding to the same sort of driving changes in greenhouse gases, and they all get different cloud changes. And so we know that cloud changes have some leeway in them. And so I can fiddle cloud changes in a particular way that maybe has some scientific basis, but really is just exploring an extreme option of what the clouds could possibly do, and see what impact that has on the temperature. And it does lead to a warming everywhere, but you can just about get it to warm the eastern equatorial, but slightly preferentially, and it causes massive warming up in the mid latitudes, right? And that does also fit with what the data shows. And so, were it that, so this is putting all of them combined in together, right? Were it that there was a small change in carbon dioxide, that we've got suggestions happened, and that there were some feedbacks that the model is not getting, and I've listed 2 of them, then I can get very close to my early Pliocene image. It's still not perfect, but it's pretty close. And as you can see, there's still approaching 5 degrees of warming, so I'm getting there, right? There's still not, like this is just a sensitivity study, and I've not put in all bells and whistles, and so I wouldn't expect it to get there. But nonetheless, if I throw these 2 physics changes in as well as a carbon dioxide feature, then I can get to something that looks like the Pliocene climate. And so just let me summarize. So the Pliocene was a warm climate with a different pattern of temperatures in the Pacific. And the pattern of temperatures in the Pacific really matters. You know, an El Nino phenomenon is a minimal change in temperatures compared to what we're in the tropical Pacific compared to what I'm showing here. Right? We know this world looks like it's got a similar level of carbon dioxide than we're breathing today. The only way I know of, and even then it's not perfect, to be able to replicate the observations, the paleo observations for the Pliocene, is to invoke not just one, but multiple strong positive feedbacks to a carbon dioxide increase to be able to get to that time. Now, there's something that I guess I've glossed over. There's no knowledge about the timescales at which these processes will occur. Obviously, 4 million years ago is a long time, and this state was stable for a long time, and so it could have easily taken 1,000, 10,000 years for all of these feedbacks to work through to be able to get me to my Pliocene climate state, or it could have taken 50 years. I just don't know. But nonetheless, those strong positive feedbacks are not included in the models that are doing future projections. And so I guess I'll just finish with talking of future projections. I thought I ought to show one. And so this is, again, from the summary for policymakers. And what you can see is the model behavior over the past sort of 70 odd years. And then there's 2 different possible greenhouse gas futures here. And they're given the wonderful titles of RCP 8.5 and RCP 2.6. But nonetheless, 2 different possible greenhouse gas futures. One, and the blue one, is the one that involves us very soon making a choice not to emit more greenhouse gases and to scale back those emissions. And that leads us to a world that is all the time below 2 degrees. And I don't know how much leeway there is in these exotic feedbacks that I've talked about. But I'm quite worried about them, and I certainly don't want to live in a world like the Pliocene. And so if we can avoid getting to a place where these feedbacks kick in, I think it'd be a really good idea. And so to get to that world, we need to make decisions now, not in 30 years' time. And I'll leave it there.